All right. Good afternoon, everybody, and thank you so much for joining. Thank you for the wonderful introduction, Suzanne. This is wonderful to be here, part of the Maryland EMS Society here. Well, I see some very familiar names here on the screen, so hi again. And for those of you who don't know me, I am Aditya Belwadi. I'm a research scientist and also oversee some of the child passenger activities at the Center for Injury Research and Prevention at the Children's Hospital. Okay, most of you know CHOP, but what I'd like to give a quick overview is within CHOP, we have several areas of research, oversights, and thrusts. I am part of the Center for Injury Research and Prevention, and within that, we have several areas of priorities. We focus on young driver safety, post-injury care and recovery. We do quite a lot of work looking at epidemiology, injury research methods. But my area of interest primarily focuses on child road traffic safety and pediatric biomechanics. The picture that you see there is actually one of our new buildings that we're moving end of the month. So we're all excited for that. So we do bring in a lot of passion at the center, apart from buildings and other stuff that we move to. Most of us are engineers, scientists, researchers, clinicians, epidemiologists. So we bring a wide variety of sort of research oversight. And the goal is very simple. We want to make sure that youth, young adults, and children are safe. Whether they're in cars, outside of cars, or walking, or even biking around. So I'd like to kind of break down my webinar in three broad areas. Most of you I see are kind of in the area of child passenger safety and injury prevention. So as you know, the collective we, the work that you guys are doing, researchers, clinicians, and hospitals, we've come a long way. We've truly come a long way looking at the injury epidemiology data. Fatalities and injuries as such have reduced, but it's not zero yet, and that's our goal. So what I'd like to focus on today is, we have come a long way on this road of injury prevention and injury recovery, but there is still a lot of things to do. So the simple story isn't enough. So I'll delve a little bit into the history of biomechanics, why we are doing this, why or what we should do to kind of help see the future where we can actually bring these injuries to zero. So a quick overview, if you look at the data from the World Bank Transport for Health, this is data from 2014, children younger than 14 years of age, road injury is still one of the leading causes of fatality by age group. So if you look at ages 1 through 4 beyond, and up till teenage drivers and young adolescents, you can see that road injury, motor vehicle crashes are still the primary cause of injury and fatality. This number is going down. I mean, if you look at Centers for Disease Control, this is the data from 2014, early Feb, you can see the total or the age between 0 through 12 years of age, this is the black solid line that you're looking at, is actually going down, which is great news. I mean, we have helped decrease these injuries substantially, almost 43% in the last 10 years. And this is primarily be attributed to quite a lot of things. I mean, one of the coolest thing that we can attribute to is the increased restraint use. Data repeatedly has shown that the overall percentage of restraint use has increased. More stringent highway safety laws, and then looking at the vehicular aspect of it, advanced restraint systems, airbags, roof curtain airbags, you name it. There are a whole bunch of airbags in car now. And also structural integrity of vehicles have improved significantly, causing this number to go down. If you look at some newer data from NHTSA, looking at what are called as FARS data, or Fatality Analysis Reporting System data, this is actual fatalities. You can see the number, if you kind of trace down the red line in the top plot, which is looking at ages 8 through 12 years of age, it's almost half a number in the last decade. But one thing I'd like to point out is that number is still in the 3 digits. We're not in the double digits or single digits or even zero, and that's where we'd like to get to in the next decade or beyond, is to look at those injuries. But One thing which is very interesting is some of the latest data that came out recently actually shows an increase in fatality. The overall fatality rate has actually changed by about 6% in children under 16 years of age. And there are several different attributes to it. Most people associate this with improving economy and reduced gas prices. So you actually see a lot more vehicular density causing vehicles to interact more often, leading to fatalities or injuries. But obviously we need to do more research and sort of understand what are the complex nuances to interaction and understanding that it's not a simple solution. There is complex entities going beyond to bring those numbers down. So if you look at the last 30 years, if you kind of pay attention to the left pie chart here, this is data from early 1980s. The percentage, the distribution that you see in motor vehicles, that's about 36%, is still very similar. So if you fast forward it by 3.5 decades, you would see that motor vehicles still has a substantial chunk that contributes to fatal injuries and injuries as such. Child motor vehicle injury is a very, very significant problem. So with that in mind, I'd like to kind of jump along and get to how did this all start? How did we even get down to understanding biomechanics or understanding how the human body behaves to unintentional external loading? It all kind of started off in the early 40s and early 50s. Some of you have heard of the Stapp car crash conference. Is one of the premier leading conferences for our area of research. It's actually in honor of Colonel John Paul Stapp, who was at that time one of the pioneers for understanding high-speed impacts. He was a physician in the U.S. Army Corps, and he said, there has to be a better way of studying these injuries. I mean, at that time, we didn't have crash test dummies or computational modeling or other surrogates for human studies. So he said the only way I can get a better sense of this is to actually put myself in a deceleration experiment at that time using a rocket sled. You'd be surprised that he actually went from about 600 miles to almost stand still in about 1.5 seconds, experienced about 46 Gs. I'm just going to play this video. So this is a rocket sled. You can actually see John Paul Stapp strapped himself into one of these seats there. He crashes into a rigid barrier. That's actually a camera system floating about to keep a track of what's happening and how fast he's actually going through. And it's interesting, he actually obviously survived this crash. He suffered very severe retinal detachments, but he was sort of the pioneer for human studies, human biomechanics studies, really trying to understand what does it take for the human body to sustain injury. What are those limits? And obviously this was an adult study, but this kind of set the road and the path ahead for understanding what are the external forces, what are the boundary conditions, what are restraint systems. And you'd be surprised, if you take a look at this again, you'd realize he's going at 600 miles per hour and comes to a standstill. I mean, most automotive crashes today are looking at 30, 40, 50 miles per hour, and you see fatalities. So then you start thinking, how can he sustain or survive a deceleration so fast, but a 30, 40 mile per hour crash, people don't survive. So that's when we try to understand the limits of the human body and also what sorts of deceleration, acceleration forces, injury tolerances, vehicular intrusion into the compartment, airbag systems, and so on would play a huge role in sort of injury mitigation and understanding injury. So with that in mind, I'll kind of jump along to looking at child passenger safety and the first car seats out there. Some of you might still see a few in the field. I'm a child passenger technician as well, and I see all sorts of seats in the market today. But thank God, we see some newer models out there and people actually doing a good job installing. Some of the earlier seats were literally, office chairs which were strapped on cars tied with ropes and other systems to protect the child. It wasn't a bad design, but didn't really do a good job. And we've seen that we've really come a long way in safety. I mean, that's how things were in the early 40s and 50s, almost as a hoop sort of a mechanism going over the car seat. But Volvo in the early 60s was sort of pioneer in coming up with the 3-point seat belt. And since then, things have really sped along in terms of regulations, CPS laws, some advanced testing surrogates. We're going to talk a little bit about anthropomorphic test devices, or dummies, or ATDs, and how NHTSA and the Department of Transportation is playing a huge and a fantastic role in trying to understand these injuries and coming up with relevant laws to mitigate those systems. So in trying to understand crashes, one of the first things we really need to pay attention to is what are those injury mechanisms? What are those stages in a car crash? And for those of you not very familiar, a single car crash actually consists of 3 broad collisions. The first collision, if you think about it, is the actual vehicle impacting the object. This could be another tree, another car, another system as such. So this is the very broad crash dynamics that you're looking at. The second collision that's happening is the occupant kinematics. This is when the actual driver or the passenger or the occupant interacts with the vehicle structures. And these could be seat belts or airbags, or he or she is not restrained. It could be the steering wheel hub, or even the passenger compartment, or the seat in front of you. Now, the third collision is something that we don't really see or observe immediately. This is what is called as impact biomechanics. This is internal organ motion. So if you kind of think very broadly, you have your vehicle hitting, say, a tree, you have your occupant impacting the hood or the vehicle structures as such, and then you have internal organs. So you have your brain moving within your cerebrospinal fluid, impacting the front of the skull or the back of the skull. That's where we see contusions, coup, contra-coup injuries. You have your internal organs, your heart kind of moving forward or backward based on the direction of impact, colliding against the internal rib structures, the sternum, the aorta moving around, causing aortic tears, aortic lacerations. So it becomes very, very challenging, and trying to understand how to mitigate these systems or these organ motion is almost impossible. I'd love to hear your comments and your questions as to how we think we can actually reduce this impact. But as an engineer, we go back to understanding collisions 1 and 2. So is there a way we can control these dynamics? Can we control this impact? So for an example, if you have a car turning opposite, I'm going to play this again, go back and play it up. There you go. So if you have a car making a left turn across the opposite or oncoming lane, this is one of the most common types of crashes. You get hit broadside by an oncoming car. And the types of car, the relative sizes of these vehicles, whether it's a small sedan versus a truck, whether it's an SUV versus a small sedan or a mini car, plays a huge role. Speeds and directions. And, going back to the laws of physics, it's about conservation of momentum. Objects with higher mass has lower velocity in collision. So the energy transfer is basically transferred to the smaller vehicle. And you can actually see those deformation patterns. So as an engineer, we go down to the scene, we look at these deformations, we kind of understand, okay, obviously there was nobody there to tell us firsthand. So this is sort of post-crash analysis, or accident reconstruction is what we call, looking at how did this door structure collapse, what sort of structures can we build around it, maybe airbags, maybe strengthen the system, which can actually mitigate intrusion or structures coming in contact with the occupant. The second collision is occupant kinematics. This is where you would really play effort into understanding how dummies, or in this case, actual occupants, could be kids, could be adults in different seating positions, and how they move. What are their initial positions? Were they restrained? Did they have their arms outside? Different seating positions. And you can actually see the video here. The video on the left is looking at unrestrained children. This is a video from the Insurance Institute of Highway Safety. Obviously, you won't have a child driving, so it's just an example here. But these are unrestrained kids. both in the front seat and in the back seat as an example to kind of understand how kinematics are. And just this is obviously full frontal impact. A minivan, you can kind of see where these kits land up, impacts the passenger airbag, impacts the windshield, very severe injuries, of course. And now another example is looking at a kid seated in the back seat. This is a 6-year-old dummy in a high back booster seat. So the kinematics is a lot more controlled, restrained. Obviously, the head doesn't hit the front seat. If you kind of go back and look at these data again, whether we're looking at accelerations or deformations or any sort of kinematics as such, we then look at did they contact the side doors, did they contact the front door structures or the front seat, and then understand how can we do a better job. So it's a constant process of improving these kinematics, so based on seat designs, based on internal geometry, based on airbag systems, it's a constant process to make sure that the third collision, the injury biomechanics piece of it, doesn't really happen. So the first step is to make sure that we don't really see a whole lot of tissue damage or organ damage or say fractures and so on. There are some things that can be fixed very quickly. For example, if you have I'm just giving an example of a femur bone. This is your thigh bone. This is one of the longest bones in the human body. A femur fracture is relatively faster and simpler to fix. Again, I'm not undermining the injury than an internal organ injury like your brain rotating about in the cerebrospinal fluid and impacting the front of the skull, which is sort of an internal injury and quite difficult to sort of diagnose and treat as quickly as possible. So that's where we kind of start going back and seeing, can I reduce my collision, number one and number two? Can I build better systems, better vehicular structures, better crush zones? Say additional airbags. You have, some of you might have driven in one of fancier new cars where you have side airbags, side torso airbags, you have knee bolster airbags, you have front airbags. Hopefully it hasn't deployed anytime soon, but it's about distributing that energy in a larger surface area and making sure that there is very little to or no energy transferred to the human body. That's where computational modeling comes along. So we can take care of collisions 1 and 2, but how do we really understand what is happening in these organs? How do I go and take a look at for example, the aorta? So what you see on the right side is the aortic arch. As you know, the aorta is one of the main pulmonary arteries which supplies oxygenated blood into the rest of the arterial system. The 3 superior vasculature which go up supply blood to the brain, and the superior or the descending aorta, which you kind of see the arch going down, supplies oxygenated blood to pretty much every other system in the human body. So what you see is on the left, you can actually see the internal structures of, in this case, a 4-door sedan being hit on the driver's side by a SUV, which is almost about 3 tons in weight. You can see the amount of intrusion, the seating structures, the sort of the steering wheel getting deformed, and this is basically a cut through the center to give a sense of what really is happening inside the vehicle. We then take human body models, put it in this exact seating position, and in this case, I was looking at a fatal aortic injury. That is, in this particular case, this is a real-world case that we simulated, trying to understand in this instance of crash, what really is happening to the aorta. Aortic tears or aortic lacerations, if that happens, the heart is still pumping the blood, so you have blood pooling into your chest cavity, or what is called as exsanguination into the chest cavity. This is a very quick process, and unfortunately it's quite fatal as well. I mean, there's not much EMS or anybody can do. So we really want to understand, in this particular example, what was happening to the occupant, and can we design better systems, better, as you can see, there's no airbag in there, there's no side airbags. Can side airbags help the system? Can a better internal structure, better seats, sort of help us understand or mitigate these issues? So on the play, so we then start questioning ourselves, how different are kids and adults in car crashes? Obviously, these are examples of photos from a colleague, and definitely not my capability of doing these dances. I have 2 young kids. I'm sure they'll really enjoy seeing these pictures. But kids have a substantial flexibility. That's because of their anatomical differences. Their size, their anatomy, skeletal structure, their material properties are still lax, be it bone or ligaments. This all leads to flexibility, which is much different from adults. And one thing we always keep saying in our field is kids or children are not young adults. That's a differentiating tool for us. Is you cannot really take adult data, be it a 50th percentile human or a 35-year-old male, and then scale it down based on size or age, and then say, okay, now let's use this data for kids. It doesn't work that way. We really have to understand their both anatomical development and physiological development, and how kids sit, how kids move, and their injuries are, I wouldn't say substantially different from adults, but they are different. They're based on what sort of tolerances you have, what sort of impacts, or what sort of external forces lead to injury. And it becomes challenging to understand pediatric injury is you don't have a good surrogate to study pediatric injury. So we do have pediatric crash test dummies, but there are some drawbacks and some challenges associated with this. So what other tools? So crash tests with PMHs, that is post-mortem human subjects, have been extensively done for adult research. Thankfully, no specimens, and we don't do any of that work as well. Animal studies, yes, there are quite a lot of animal studies out there using different surrogates, pigs, bovine, porcine, but it's very difficult to draw sort of an age equivalency to, say, a young 2-year-old or a 3-year-old, and that's something that we don't do either. The other thing that kind of comes down to is human volunteer tests. Really? Is that what we end up doing? To some extent, yes. So this was a fun project that we did for work. And how often can you actually go to an amusement park for work, right? So we actually went up to Six Flags in Jackson, sat in one of these bumper cars, instrumented these cars with load cells, force gauges, and accelerometers, drove around for a little bit, figured out what are those impacts, what are those acceleration, deceleration pulses that we see for kids. And these are kids 6, 7, 8-year-olds and younger too. And then we got back to our lab and actually reconstructed a similar setup, a similar bumper car setup. The picture on your left actually gives you an example of that. We have human volunteers. This was actually a project that was led by my director, Christy Arbogast. So thank you to her for her slides. And what you see is a human volunteer who was, I believe, 6 years old at that time, and he's seated on a simulated bench setup with instrumented load pans, force gauges. We're measuring foot pan loads, and what you see, all these little marker systems. These are called Vicon markers, and you might have seen some of these in Hollywood movies like Avatar and all those other movies where they do face capture and transfer that to a computer model. That's sort of similar to what we're doing. We're actually having markers set up on bony landmarks. That is, we have markers on the wrists, the elbows, we have some on the ankle and the knee joints, we have some on the head, and what we do is we actually track them in a 3D scale. So you can actually see a picture on the right looking at how these markers translate the human body motion into kinematics. I won't go into detail into the rest of the study, but we ran several systematic evaluations between young 6-year-olds, 8-year-olds, young adults, and older adults, and compared the responses. And if you kind of recap some of the slides from before, I said kids don't move as similarly as adults. And that's exactly what we found. They have a bigger trajectory. And if you trace this black line here, that's the head top motion of a kid in a low impact. This is a bumper car impact. And immediately you might question, hey, this is a bumper car impact. It's probably less than half a mile per delta V change. But in an actual crash, we have close to 30, 40 miles per hour delta V. How do we sort of correlate this data? That's where computational models come along, is we take this data, plug it into computer models, and then run those computer models at 30, 40, or 50 miles per hour delta Vs and try to understand what really happens in higher speed or higher impact crashes. So as you can see, the kid moves further forward. This is a 6-year-old compared to a 30-year-old. So their trajectories are longer, the trajectories are more broader and further down. And what this tells us is they have a lot more flexibility, the spinal flexibility, their anatomy, the way their cervical, thoracic, and lumbar vertebral bodies are set up are slightly different than a 30-year-old whose vertebral changes have stopped, who is matured enough that their vertebral angles, the facet joints, or how these vertebrae are actually connected, are more settled in. So there's a lot more laxity, flexibility in a younger kid than compared to a 30-year-old. Now, if you take this data and kind of bring it back into your world, you would immediately realize that if a 6-year-old is in a booster seat, who is seated higher up and moved forward, is in the back of a car, he has a potential possibility of contacting the front seat or the door structure because they're a lot more flexible. And that's exactly what we do, is to sort of translate this data back into real world dynamics. Most vehicle manufacturers, child seat manufacturers, don't do volunteer tests, or they use a crash test dummy or an ATD, anthropomorphic test device, or a test dummy. And what really happens is these dummies are similar. Anthropomorphic means human-like. They are similar to a human, but they're not really human. They don't have those responses. They don't have internal organs. They're not as flexible. If you look at the picture on your left, you can clearly see that the spine, the cervical spine, is a big black structure, which is, it doesn't have the individual vertebra. So their rotations, their flexibility is a lot different. And as you can see, the dummy is the dotted line, and the solid line is the child itself. So there are subtle differences in how the dummy moves and how the child moves. And what I'm not saying is, dummies are not bad. They're actually great tools to study this motion. But what we are trying to do is to constantly improve these dummies. And why do we want to improve these dummies? Because these are the dummies that actually help certify manufacturers, vehicle manufacturers, child seat manufacturers, in adhering to the Department of Transportation standards and making sure these seats, these car seats and child seats, are actually representing real world or mitigating real world injuries. So we actually make a small constant improvement every single time new test data is released. So with that in mind, I'm going to jump over and spend a little bit of time on some of those research studies. We're kind of doing well on time here. Yeah. So as I said before, the simple story isn't enough. What we need to do is really make a dent, get down into precision prevention. Is what we do is sort of understand research-driven change for safer roads. We go back to real-world data. We interact with clinicians, interact with vehicle manufacturers, interact with child seat manufacturers, and say, what is it? What is that concerning problem that you have that we can help make a difference? And one such project is quantifying CRS fit. As a technician, you would always face this problem, I'm sure, when you're helping parents, caregivers install their seats. Either the seats don't fit in properly, you have to move the front seat, you have to move the side seat. Pool noodles, very common and very popular. But why is it that we have to struggle to install a child seat in a vehicle? Shouldn't automatically kind of fit in there? I mean, if you look at what's happening in the market today, car seats or child seats are getting bigger and bigger. Side impact protection, trying to accommodate for bigger kids of the same age, same size, going up to higher weight limits. We saw some at Lifesavers going up to 50, 65 pounds. And however, if on the flip side, vehicles are getting smaller and smaller. They're accommodating for EPA regulations, gas mileage, city driving. They're getting smaller. Car seats are getting bigger. As a designer, designers, both vehicle manufacturers and child seat manufacturers, have you taken into account occupant protection, comfort, spaciousness, and obviously meet with all of the regulations and consumer metrics out there. So it becomes very sort of difficult to understand this interaction or compatibility. And what do people do right now? Both vehicle manufacturers and child manufacturers actually pick up a few seats from, they go to a brick and mortar store, buy a couple of car seats in the market, go install it in their vehicles in a parking lot. And we did a quick assessment. There are close to about 300 vehicles, makes, models, variations in the US market as of today. There are about 290 or close to 300 car seats. So if you do a full factorial analysis, that's about 90,000 installations in different seating positions, right? And it doesn't end there. If you have a 6'2" driver who likes to push their seat all the way in the back, you're squishing your car seat in the back. It's going to lift up if it's a rear-facing seat. There's hardly any space there. And it's obviously a time-consuming process, and it could take forever. There are some things out there. Some newer car seat manufacturers and a lot of other manufacturers now scan their car seats and bring it into their digital world. But there's only so much you can do by scanning current vehicle models. It's not sort of future-proof. So this is where we kind of said, how can the collective we, child seat manufacturers, stakeholders, vehicle manufacturers actually help understand this design process better? So this is when we actually started scanning and bringing in several car seats in the industry and trying to create what is called as a virtual surrogate. In my presentations, this is where I typically ask the audience to lift up their hands and say, have you ever used an Xbox Kinect sensor? If you have, if you're one of those fans with an Xbox Kinect, you've probably interacted with a Kinect sensor. This is what, this is a tool that you use, you move around and it actually recognizes your skeletal system. What we did is we actually took a Microsoft Kinect Xbox sensor, converted that into a handheld scanner. It's pretty cool, actually. So you can actually walk around a car seat, it scans it in real time, converts it into a computer model that you can then bring it into a design environment and make changes to it. So it's pretty quick, gives very high resolution and very low cost as well. It costs about $100. So what we did is we scanned every single car seat in the US market. And the video that you see in front of you is an example of a rear-facing child seat. We brought in all the rear-facing CRSs. You can see this includes infant seats, infant carriers, convertibles, which are in rear-facing, with base, without base, cup holders, moving the handlebars at different positions, moving the hood all the way up front, all the way back. We installed them as per manufacturer recommendations. And installation means this is a virtual installation. Those planes that you see, the green plane and the sort of orangish hue yellow vertical plane, those are seat pan and seat back angles of the average US second row seating position. So this is data that we got from the literature. So we brought in all these seats, overlaid them on top of each other, and started converting them or creating what is called as a blob. So we bring them, wrap them around. It's almost wrapping a gift. You take a non-uniform object, put a wrapping paper around it, and then put it in a box. That's exactly what we did. So we took all these car seats, converted or wrapped them, shrink wrapped them, and created bounding volumes and created a virtual surrogate or a blob. So I'm happy to say this is one of the largest studies that we have ever done, comprising of close to 300 child seats in the US market. Pretty much every single car seat out there as of last year, including some of those newer car seats with wheels and so on. We got them all. So what we did is we then started classifying them into rear-facing, forward-facing, high back boosters, low back boosters, and started creating bounding volumes. And one of the advantages we have is we worked with both the vehicle manufacturers and the car seat manufacturers to decide how big this volume should be. It's not just a representation of current seats in the market, but with bounding these blobs or creating these surrogate models helps us to sort of look into the future to also understand what sort of new models car seat manufacturers are coming out. So this helps us define a box around it and give this virtual surrogate to manufacturers to actually help them install it in their internal installations and systems. So this is a virtual installation ahead of time. So with this data, vehicle manufacturers can then go back and look at their car seats and also understand how car seats fit in their current design. we are in 2017. Most vehicle manufacturers are already looking at 2020 vehicle model years. So this data really helps them and is actually helping them right now to design these interactions internally. And what does it do to us? As a consumer, as a caregiver, as a parent, it really helps the end user. And that's our goal, is to help the moms, dads, caregivers, and parents to really get that right fit in their vehicle that they have. So, they don't have to go get a seat from, say, Amazon, bring it home, and then realize, hey, this doesn't fit in my small car. I either have to return it or I'm just going to push it in there and keep going. So we want to make sure that we get the right car seat installed correctly every single time. So I'm going to jump along and talk a little bit about I see a few questions coming along, so I'm going to answer them as I kind of go through these slides. Hopefully I can get to answer all these questions in the end. So talk a little bit about side airbags. We talked briefly in a couple of slides about how we need to mitigate or understand these collisions. Collision number one is the vehicle actually impacting a structure or another object or a tree or so on. Collision number two is actually sort of mitigating and understanding occupant kinematics. And this is where airbags come into play. I mean, we are all familiar with different types of impacts out there. You have frontal, you have side impacts, you have rear impacts, rollovers, and other different scenarios. But as you see, almost frontal and rollover crashes have the highest number of fatalities. And the way you read this graph is the left vertical axis. The left axis is number of fatalities, and the bars kind of read to the left, and the blue line that you see reads to the right, which is the fatality rate. So the fatality rate is the probability or the risk of dying in a particular type of crash, and it's one of the highest in rollover crashes. In the next couple of slides, I'll talk a little bit about side impacts, those little maroon bars that you see looking at right side and left side impacts. Just to give set the kind of the playing field even here. So if you look at the actual vehicle up there, looking at the hood itself, whenever you hear 0-degree impact or 360-degree impact, it means it's a full frontal impact. A 90-degree impact, so this is almost like a clockwork diagram. A 90-degree impact is impact to the right side of the vehicle, 180 is a rear impact, and 270 is to the left side, which is basically where the driver is seated. Near side is if you get hit at your seating position. Far side is if you get hit on the opposite side of your seating position. So here's a quick video before we look into side impact of IIHS, or the Insurance Institute of Highway Safety, testing some of their vehicles. This is called a MW moving deformable barrier, which is usually set up at about 40 miles per hour. It has a slight angle to it to sort of replicate this issue of, you see a car coming towards you, you brake, you swerve, so it doesn't hit exactly, it's almost like it's not a T-bone impact, so there is some amount of angle there, which is called a crabbed. So this is coming in at about 40 miles per hour, impacts near side to the driver. And I don't know if you can see there's an airbag which deploys. There are dummies seated near side as well, which are instrumented, which are measuring different data, accelerations, deformation in the head, in the chest, in the pelvis. There are sensors on the door panel which measure sort of door intrusion velocity. Here's a view looking from inside. And most dummies are actually painted, and that's a cool thing to do, is to really understand where the dummy hit the airbag. You can see the paint marks left on the airbag itself, and sort of pay attention to how deep the airbag deploys in the front and the back seating position. You can see it doesn't come all the way down to the window sill or to your armrest. So it deploys about 1.5 feet into your seating position, primarily sort of protecting your head-neck complex. So airbags were introduced back in the early to mid 1990s. There are several different types of airbags, but what I'm going to talk today quickly is looking at side airbags or side curtain airbags. These are airbags which are mounted in the side roof rail. So the next time you sit in your car and you look up onto your top left, you can actually see, it's actually written in most vehicles that it says side airbags, or SRS, or Supplemental Restraint System. According to NHTSA, some of the more recent data shows that near side impacts are pretty critical in terms of both the injuries that you sustain. AI is 3+ injuries. This is primarily looking at children under 14 years of age. The blue vertical bars are impacts near side, that is near side to your seating position. And then the maroon bars are center and the green bars are far side. And right away you can see based on where it gets hit. So near side, definitely you have a higher probability and higher number of injuries, because all that's separating you and the other vehicle is about 6 or 7 inches of door structure, correct? And then you potentially or hopefully have an airbag that deploys between you and the intruding door structure. So we wanted to systematically understand how side airbags and side curtain airbags play a role in sort of understanding where it gets hit, type of injuries, and what sort of injury prevention that we can do. So we quickly looked at the real world cases. This is a siren database. This is called the Crash Investigation Research Engineering Network database. This is one of the largest real world crash data system out there, which gives details into again, we pulled up only the child seat data. So this is where was the car seat installed, how was it installed, where the occupant was seated. We looked at kids 0 through 19 years of age and then sorted them out based on age, seating, location within the car, whether they were in the front right seating passenger position or the rear seating positions, whether they were near side or far side to impacts, were they near side to a deployment, and so on. And then we sat down as a team and looked at contact points. So we defined contact points. Did the head hit the roof? Did the head hit the side door? Did it hit the side curtain? And came up with what is called as a contact map. This is just a nomenclature of how these maps are set up. The solid dots are left impacts. The dots with a circle are right impacts. And if you have both the left and the right overlaps, it's sort of a dot within a dot. So what you're seeing here is an outlay of a vehicle system. So this is the right front passenger seating position, and you can the sort of hazed out diagram is where the bag actually deployed. This is average deployment heights for different vehicles, and then you have the torso bag, which is sort of circled out and oval. And the goal behind this was sort of simple, is to understand where do kids, if this is, for example, a front right seating position, and we primarily, and thank God, we saw only kids beyond 9-10 years of age. We didn't really see any kids in car seats or high backs or booster seats. We actually saw if there were any cases in there, and I would say we were lucky we didn't get any of those cases. So these are primarily young adults between 9 and about 16 years of age. And if it says LE or UE, this is upper extremity, lower extremity. S is the spine, T is the thorax. As you can see, there are really not a whole lot of head injuries. So these are all restrained occupants. Now, if you look at the rear seat, it's sort of interesting that, again, this is the rear seating position behind the passenger side. Again, most cars didn't have a torso bag. This is just a roof side rail mounted bag that was deployed. Keep in mind, these are all young kids who are in a car seat, either high back booster or a forward facing. There were just 1 or 2 cases with a rear facing infant seat, and none of them had any contact with the door structure, which is very interesting. But most kids seated in whether a high back or a forward facing seats did have some contact. So H is head, A is abdomen, T is thorax. You'd be surprised how high they actually move and impact based on the geometry or the impact angle and the location. We said, okay, now we're looking at real world data, but we obviously have to test further for different conditions. So we did a bunch of side impact tests and ran or compared high back booster seats with low back booster seats and no CRS conditions. And let me kind of walk you through this video a little bit. And the reason why you kind of see this as a hazy video is not because it's hazy, because it's sort of overlapped with the high back and the low back seat. And as you can see, there is no side airbag being deployed. So if you look at the top left picture, it is a combination of, let it come back. Combination of a hybrid 3 dummy. I'm not going to go into the types of dummies itself, but a hybrid 3 dummies with a high back and a low back seat. And then on the right side, it is a Q6 dummy, which is a slightly different variation of a dummy. Both are 6 years old. These are 6-year-olds restrained in a 3-point lap shoulder belt in a high back and a low back booster seat. And what we're trying to look at is head contact points. These are again painted on the side to see where they actually hit their heads. This is a T-bone impact, sort of a 90-degree impact, and the impact pulse is sort of real world. This is slightly higher than real world testing standards that we are seeing. We ran a bunch other tests looking at side airbags. This is a side curtain airbag. The positions, the deployment types, the deployment timing, angle were all set up to a real world 4-door sedan. So this is a rear internal door structure, a rear second row seating position with a high back seat. As you can see, there's a wing structure there. This is a 90-degree impact, almost sort of T-boning into the rear seating position. This is a low back booster seat. Again, no backrest with a side airbag deployed. And you can actually see paint marks being transferred onto the airbag itself. We did run one other condition. We kind of wanted to see what really would happen if you kind of now sort of eliminate the booster seat itself and just run the 6-year-old in a side impact to understand contact points and locations and injury itself. So I'll quickly kind of jump to the results. We did several FE models or finite element models of human data. One thing that we saw was side curtain airbags in general aided reduction in head and chest acceleration. So if you do have a side curtain airbag with high backs or without high back seats, there was a reduction. However, there was a slight increase in some of these pelvic Gs. Again, this was not a significant finding, but more sort of an artifact of how the testing was set up. But in terms of CPS and how this is related to, is we are talking or looking at side airbags or side impacts in general. You know, in your curriculum itself, we predominantly focus on frontal impacts and predominantly frontal modes of crashes. But what we're seeing is we kind of now want to expand into other modes of injury in other directions as well. And it's sort of interesting and important to understand what really is out there, what type of seats, what type of airbags out there. And what we saw was very interesting. High back booster seats have similar injury responses as low back booster seats when exposed to a deploying side airbag. So if you have a side airbag, similar impact conditions, high backs and low backs provide similar protection. But if you don't have a side curtain airbag, the ATD sort of consistently displayed higher injury numbers for low back seats as compared to high back due to its interaction with the intruding door as such. One thing to keep in mind is most vehicles today, almost 98% of the vehicles in the US market have a side airbag in the rear seating positions. Whether it is add-on as an additional option that you have to buy or pay extra or comes with it as a standard default structure is really up to the consumer because it's not a mandatory standard out there. But there are some older vehicle models with no side airbags as such. Again, keep in mind this is just a 90-degree impact that we tested, pure T-bone impacts. And some of the other work that my colleagues have been doing actually show that in oblique impacts, now if you sort of recreate this braking scenario and swerve away, you would see that there is not a whole lot of injury prevention coming up with these wing seating structures as such. So kind of jumping quickly, I know we're kind of running out of time here, so we'll quickly talk about one other important topic, is kind of looking at rear-facing infant seats versus convertible seats for kids under age 1. I'll quickly talk about some of the recommendations that came out, I think early last year by Consumer Reports, is sort of this recommendation to transition to a convertible seat at age 1. And I know we at SERV, we got a lot of questions and confusions about what really is happening. Should we move the kid around forward facing and so other things? But no, what Consumer Reports really said is you transition them to a convertible seat, but still rear facing. And why did they say this is they ran a slew of sled tests and with a 12-month-old child dummy called the Krabby dummy. So the picture on the left is a picture of an infant seat and the picture on the right is a convertible seat, exact same dummy, same weights, installed in similar seating positions. And what they found is in infant seats, or rear-facing infant seats, they found that the top of the dummy's head contacted the front seat back almost 53% of the time in infant seats, as compared to about 4% of the time in convertible seats. Again, these are simulated sled tests. And why that is important? Because we're looking at head injury. We're looking at the amount of space in the behind the child's head, and the likelihood of head contact with the front seat plays an important role. We talked about how kids are very flexible, their head motion, their head trajectories are longer. And convertible seats as such, most of you are very familiar with these seats, are slightly bigger in size, and they provide this additional space behind it. So what is our recommendation? Obviously, kids under age 2 are safest when restrained rear-facing. This remains true whether parents, select an infant seat or convertible seat, both rear-facing. And again, a change in seat, whether you go from an infant seat to a convertible or a 4-in-1 or a 3-in-1, doesn't mean change in orientation. I think that was the confusion that came out is, should I change the orientation? You still orient them rear-facing, as long as they are within the weight and height limits recommended by the child seat manufacturer. So with that in mind, kind of bring this to a conclusion. What I really want to highlight today is, I know what's really important for us, for you guys, for the industry consumer partnership, is to kind of bring down these injury numbers. We're talking about 750 to 800 fatalities every year for kids under 14 years of age in the country. So what we really want to find is this common achievable target goals that can help mitigate or bring this number down. And we need each other to make a difference. We need technicians, we need child seat manufacturers, vehicle manufacturers, stakeholders to play a huge role in mitigating this. And this is where precision prevention comes into play. That is, a simple story is not really enough. This is a slide that I borrowed from our director, Flora Winston, and what she says is, we are all sort of zebras out there. Everybody is uniquely different. If you look around, computers, tables, these boards and monitors are all mass produced, but each one of us are completely different. Biomechanically we are different. So what works for me may not work for you. So we are kind of getting into this phase in safety prevention where we're getting into precise, sort of almost like a drug delivery system. We need to precisely fine-tune, seating positions, seating postures, come up with realistic or naturalistic ideas of how kids and occupants sit, and then design or devise systems which are very specific to occupant size, shape, and use. So my kind of message is, think precision prevention. That's where we need research interventions to kind of meet the specific goals of injuries and individuals. So do stay in touch with us. You can subscribe to our blog at injury.research.chop.edu. You can also get more information on some of these projects which are published out there at CCHIPS, which is CCHIPS, the Center for Child Injury Prevention Studies, cchips.research.chop.edu. So before I close, one quick video on where does safety stands today. This is a video by the Insurance Institute of Highway Safety. The car on the right is a 1959 Chevy Bel Air, and the vehicle on the left is a 2009 Chevy Malibu. Same manufacturers, almost similar platforms, almost 40 years apart in generations. Pretty brutal impact. This is a frontal offset crash, about 40 miles per hour delta V. Both have an instrumented crash test dummy. What's really interesting is the interior or inside look of what's happening to these vehicles and to these dummies. I hope this is still playing. Oh.
In other words, we've come a long way.
We've come a long way.
Automotive technology and occupant protection.
Oh, there you go. This is really interesting. This is the 1959 Bel Air. You can see the amount of intrusion that's happening. Everything comes apart. The dummy contacts the hood. The roof comes in. Obviously, no airbag. And definitely a fatal injury for the 59 Chevy Bel Air. This is the more modern Malibu. See what happens. The airbag immediately deploys. Almost nothing's flying inside. There's hardly any intrusion into the occupant compartment. Looking at the numbers itself, the dummy was very safe. Head injury well within limits. So we've truly come a long way, and there's still much to do in terms of injury mitigation. And I'd really like to thank my team, both at Stapp, our collaborating partners at Ohio State, and all the industry mentors. I mean, without you guys, it's really almost impossible to do this kind of work, both in terms of research, mentorship, and funding and beyond.